Okay, well, I'm going to start recording. First of all, I'll share the screen. I'll make you guys bigger, put you over under that window over there. And now I can see your faces nice and large. It's a little scary, but I wanted to talk about the Coriolis force because the other day we talked about the Coriolis force in terms of a u velocity. So I'm not going to go through that again with you. Obviously, you have it on the recordings. I hope the recordings have been proven good for you. Where are you guys? Okay, but you're basically saying I have in the sphere that I've got going on of the Earth, and when I have a sphere like this, you know, we can kind of look at the equator being that way, and we were talking about some velocity going in the u direction. And so when I'm going in the u direction, what I basically am doing is I'm looking down at the North Pole. Okay, so here's the North Pole, and the u direction is actually going to be in this direction. Okay, and so what I'm saying is I have an outward directed centrifugal force. So when I look at what the centrifugal force is, and where does which way does the Earth's centrifugal force point? Which way does the centrifugal force of the Earth point?
Outward from the axis of rotation.
Outward from the axis of rotation, right? So when I'm looking at this, I'm going to have a component when I'm looking down at the North Pole that is going to be to the right of the motion. That becomes the Coriolis force. But because the motion also has, you know, because I take this vector that's outward, I can also consider that I've got a vector that is going to go to the right of motion and one that is also going to go up, right? So that I have a vertical component of this outward directed centrifugal force when something is traveling in the u direction, in the zonal direction. And what I'm basically saying is this: because I have an outward force from the axis of rotation, if I'm just standing on the Earth, it was also going to have an outward force if I'm going around latitude lines in the u direction. So that's what we did the other day. But now the question is, well, what happens if I, instead of going this direction, and let me just draw this in here, what if I'm traveling in the v direction, which would be on a longitude line? Okay, so that is a v velocity, which is traveling on a longitude line toward lower latitudes. And so what that looks like from an overhead view is that the motion is actually toward the pole. Does that make sense? The motion is going to be toward the pole. So what I can say is I want to deal with the conservation of what? What is conserved with moving objects without a force?
Momentum?
Momentum. Okay, so we have the conservation of momentum. We know that that's the case. If there's no force, there's no change in the mass, there's no change in the velocity. Okay, so momentum is, we're saying that we have m times the velocity at 1 is going to be equal to m times the velocity of 2. But here's the thing. Do you understand that because I'm on the spinning Earth, so let me draw it like this. Because I'm on the spinning Earth, I actually have a u velocity. I'm going around this big circle. And when I move to the north, I'm going to be going around a smaller circle. Does that make sense to you? Because I'm not just moving to the north. In an absolute sense, I'm going around in a big circle because I'm on the Earth. I'm on some latitude line, and then I go to another latitude line. So what is the velocity? And what I want to do is I want to kind of draw the velocity vector as being this way. So that is the velocity at 1. Now the mass doesn't change. So what that means is that the velocity, the velocity at 2 needs to be the same. So that is really the tangential velocity, right? So an object that's moving to the north has a very complex motion. It's moving to the north, but it also has a velocity that is moving to the east because it's on the spinning Earth. So the velocity, when I go back to here, is actually going to be the mass of 1 times omega, well, yeah, no. I should do it this way. RA1 is equal to the mass, I don't need to put a 1 in there, oops, times omega times RA at 2. Because the rotational frequency of the Earth is capital Omega, the mass is still the same, and now we have RA1 and 2. So we're basically saying is that when I'm here, or when I go to here, I have a radius, and I have a radius. This is RA1, this is RA2, remembering that RA is equal to RE cosine phi. You guys remember that?
Mm-hmm.
So what's changing when I go to the north? Well, the radius of 1, let me do it this way, the radius of 1 becoming the radius of 2 is smaller. Because this is an equation balanced, and I don't have to worry about mass, what that means is this number is going to have to do what?
Get larger.
They're inversely proportional.
It needs to get larger, right? So how does it get larger? It acquires a drift. So what I'm basically saying, and maybe I should have used little omega here, is that I'm going to have the Earth's rotation plus a velocity, a u velocity, times RA1 equals omega times RA2. And we call this a westerly drift, right? Because you're moving from the west. That's what westerly means. Now this is the Coriolis force, as though you were on a merry-go-round or a little place on the playground where you throw the ball and it goes to the right. This is actually far easier to understand because your angular momentum, and that's what this is, mass times omega times r is equal to mass times omega 2 times r2. This is a statement of the conservation of what?
Angular momentum.
Right? This is the conservation of angular momentum. Even though we understand that the velocity is omega r. So that's what the conservation of angular momentum is. So that's really what the Coriolis force does. So before I go on, does this make sense in a physical term of what has to happen as something travels to the north? So if it's traveling to the north, like over here, it's going to turn to the right. Now, if it's traveling to the south, over there, it would also turn to the right because now it's going slower, and so you need to slow its speed because angular momentum is still conserved. So the Coriolis force on a meridional velocity will always turn in the zonal direction. So stop here for a minute, take this in. What do you think? Does this make sense to you? Give me some feedback here, guys.
In the zonal direction.
Are you asking a question?
Sorry, I knocked my microphone far away from my mouth. You said the zonal direction, right?
Well, that's what this westerly drift, right? So I have a velocity of something moving purely meridionally, north and south.
Mm-hmm.
But I get a drift to the east if I go to a smaller radius because I have to speed up to maintain conservation of angular momentum. Any questions? Are you okay? Do you need to ask me something? Do you want to talk about it? What do you talk to me? Again, I'm just asking for your feedback.
I think I'm good.
How are the
Thank
rest of you guys?
I guess the way I kind of wrote it down is the Coriolis force kind of exists to conserve angular momentum when moving meridionally.
Yes. Yes, you get a westerly drift when it's moving meridionally. So we already did if it's moving zonally, we get turned to the right because of the outward force of the Earth. But here we're getting turned to the right because we're changing our angular momentum. So that it's a different concept for the north-south versus the east-west. But what we got to do is we need to now say, well, how much is that? So if I can get rid of all this stuff so that I can write fresh.
I have a quick question.
Go ahead.
So how would the Coriolis force compare to, like on a global level, compared to when your water is going down the drain? So it's like locally spinning.
Well, we know the value of the Coriolis force, right? This is sort of a, you've taken little other courses. So we know this is going to be 2 omega v sine phi, right? Now, sine phi is always less than 1. 2 omega is on the order of magnitude of 10 to the minus 4th. And this whole thing, unit-wise, is meters per second squared. So even if I had a very fast velocity in here, we're talking about something in the 10,000th of a meter per second squared. So when water is going down a sink, right, the only reason it's going around in a circle around your sink is because you put the water going that way. Remember that the Coriolis force is a change in velocity on the order of magnitude of 10 to the minus fourth meters per second squared. Do you realize how small that is? That means if you had a velocity, the Coriolis force is going to be 10,000 times smaller than whatever force is moving it. That's like this little arrow. You wouldn't even notice it. So the Coriolis force requires what in order to become apparent? Like, in order to actually have to experience it, what's got to be true?
A geostrophic?
No, you're missing my question.
Time?
You need time. You need 10,000 seconds to get a meter per second of velocity change. So you need time. So one of the questions that I remember I didn't want to do that. One of the questions Chuck Doswell gave me a long time ago, and this is a really interesting thing. And when I first learned it, I was so off because I said, well, 2 omega v sine phi. So here's a traditionally cool question. I have a pool table. I guess I have a thick pool table. And I have a pool ball on this side of the table, and I have a pool ball on this side of the table. And I'm going to hit this pool ball that direction, and I'm going to hit this pool ball that direction. And we know that the Coriolis force is going to cause it to turn to the right. So how fast do the balls need to go so that when they get to the middle of the table, they just miss each other? That the path of this pink ball goes this way, and the path of the yellow ball goes that way. So how fast do those balls have to go? And if I said, well, 2 omega v sine phi, those are all small things, so they have to go really, really, really fast, because that will give me a big change. The problem is, if I go really, really fast, there's no time for these balls to move. They're going to hit each other before they have any sort of force to move them to the side. So what they need to do is move extraordinarily slowly. And you could actually, if you want to do a fun, geeky thing, calculate the velocity needed to get that sort of a, look at the size of a pool ball, the size of a pool table, and say how fast do they have to go. So if you gave these balls several hours to get to the middle, they'd miss each other because of the spin of the earth. But you can't hit a ball, and so this is where the reality comes in. You can't hit a ball slow enough that it would keep going because there's going to be friction to stop it. The friction would stop a very, very slow moving ball. So you'd have to do this on a frictionless table. Now, when I start going into something like a tornado, where the wind velocity keeps getting bigger, now we're talking about the Coriolis forces on the order of magnitude of 10 to the minus 2 meters per second squared. But that's because it's very, very fast velocity. But what's the centrifugal force? It's v squared over r. And since tornadoes aren't that big and the velocities are high and squared, this is going to be like 4 orders of magnitude bigger than the Coriolis force. Which says what? The centrifugal force dominates. Once it's going in a direction, it's not going to change. There's an outward force keeping it from doing that. Water in a sink is the same way. This force is much, much larger than this force. What you would have to do is have a very large sink, completely still water, very carefully remove a plug, and then it would acquire rotation. But if you ever look, put water in a sink and put a piece of paper in it, and you'll see that paper moving around. So there's an initial velocity of the water that takes a long time to get rid of. Water has a lot of momentum that just keeps swirling around. And most of it is because the water goes into the sink asymmetrically. So that's why the Coriolis force is insignificant for something traveling on a really small time scale. So when we look at geostrophic winds, we're looking at something that's going to be, this might be 10 meters per second order magnitude. So we're looking at maybe 10 to the minus 3. That's 1,000. That's a couple of hours. 1,000 seconds. Or that's 20 minutes where we might start to see some impact. To balance the pressure gradient force, which is also very small, you're able to do that on the large scale because synoptic, when we talk about size scale, synoptic, mesoscale, microscale, it's not just the spatial scale, it's also the temporal scale. So it's a good question. That's something that we need to consider over the next 2 weeks. Does that make sense to you guys?
So effectively, the Coriolis force only applies on the larger scale.
That is correct. And it's not that it's larger, it's longer. It's not the space, it's the time. So when we have a thunderstorm, which is mesoscale, the Coriolis force doesn't start to have impact until we're in about 3 to 4 hours. So a lot of times when you do these simulations of storms, you can generate rotation within a storm with the Coriolis parameter turned off. In other words, you don't do this. You do bow echoes. When we look at the matrix of bow echoes, the stuff that we've seen in other classes where we see simulations, the bow echo will become symmetric. But if it lasts for 3 or 4 hours, then the north cyclonic couplet of the bookend vortex becomes dominant. That's something we do in the mesoscale course. Okay, so let's go. I want to continue dealing with this stuff here because I want to look at the mathematics of this Coriolis force. And this is a little bit, it's a little bit more challenging. So we're going to do this. This is the rotational velocity. So what I'm saying is I have the radius times the rotational velocity. What is the unit of this?
Radians per second.
Well, this is radians per second. This is going to be
meters per second.
velocity squared. I mean, a meter squared.
Oh,
this is a meter. That's a meter per second. This is a meter. That's a meter per second. So these are all meters per second. And then we're taking the time derivative of that, and we're saying it's 0. So what we're saying is that over the course of time, the rotational velocity times the radius is going to be constant. And we said it, so this initial one, like at V1, what is U?
V1, what is U?
At V1, what is U?
Cosine, or no?
You said that V1, right? That's from the tangential velocity?
Look over here. The tangential velocity, V1, what is the value of U?
To make sure that was the right thing to look at there.
Cosine phi?
Mm-mm. The answer is 0. Because the initial velocity is only in the meridional direction. Remember, little u, little v is relative to the Earth. So relative to the Earth, the object is just moving purely to the north. But as it moves to the north, what does it acquire? A westerly drift. So it acquires a u. But we're saying because the omega is going to be smaller and u goes up, that the total change in time is 0. This is a change in the meters per second squared. Okay, so what I'm going to do is I'm going to expand this out because look, the left side is really omega RA squared, right? That's what that is. So it's going to be the time derivative of omega RA squared plus RAU equals 0. Now, I'm going to do a nifty little trick here, a notational trick. I'm going to say that dRA dt is that.
Is it a dot over the R?
So if I put a dot over this, that dot, whenever you see this, and it happens in math or science, that's a time derivative. So that's all it's saying. So if I expand the left term, the derivative of the left term plus the derivative of the right term, write that whole thing out. What's the derivative of this?
Two omega RA?
Well, I mean, do the whole term. Do the whole term. Do you guys have it? Nick, what do you have?
Two omega times the time derivative of the radius, that donation plus u.
No,
Well,
it's going to be this.
I had.
Remember, omega
Wait a minute.
comes
this is
out.
0.
The derivative of RA squared is 2RA, but it's not just 2RA, it's 2RA times the derivative of RA over time. Right? So if you remember, the derivative of x squared with respect to time is going to be 2x dx dt. Right? Do you remember this? Does that make sense to you?
Yeah.
Everybody?
Mm-hmm.
So that's the first term. What's the next term? It's going to be du, oops, let me get rid of this, du dt times Ra plus Ra dot times u equals 0. Okay. By the way, I put this little green arrow in here just to show you that this statement, this first statement, is the conservation of angular momentum.
The entire first statement or just the bracketed part?
The entire first statement. This whole thing is the, right, because look what we said over here. See, it's the conservation of momentum. So here, James, conservation of momentum, when I use velocity is omega times r.
Oh, okay.
Conservation of angular momentum. But then we said that this is actually what it is, right?
Yeah.
So that's angular momentum. That's what this is. This is how does the angular momentum change with time. So instead of saying 1 equals 2, I'm saying the change is 0.
All right, I gotcha.
Okay. So I'm gonna erase all this. Can I erase it? Well, no, I'm not gonna erase everything. I'm just going to erase this stuff. This is where having a really big chalkboard is better because I can go to different sides of the room. So I want to get rid of all this stuff first of all. And I'm going to go back to my pen, make sure it's small. And I'm going to say du dt times R A is equal to minus 2 omega Ra times Ra dot. And what I'm saying is we set the term u, at least initially, to be 0. Because now we're taking like initial velocity. So that says du dt is equal to minus 2 omega times Ra dot. So I'm saying the time derivative of this u, when we start out at 0, we're going just meridianally, is going to be equal to minus 2 omega times the radius change over time. And that, what is this? What is this?
A zonal acceleration.
That's a zonal acceleration. Nick, you are one smart dude. Do you know that?
I mean, u was
Right?
zonal velocity, but yeah.
Right. So the velocity change over time, right? But sometimes people just like, oh, I'm getting so confused. So the zonal acceleration is minus 2 omega times Ra dot. Okay. So what is Ra dot? which we know to be the change in time of the radius. How fast is the radius changing?
So we're saying the difference between RA1 and RA2.
The change in R is going to be equal to the little velocity times the sine of the latitude. V sine phi. Little, but keep in mind, and I know this is a pain in the butt, this is, just so you know, this is little v, which means it's the meridional component of the full vector v. See what this becomes. Oops. Now you'd look at yourself and you'd say, well, wait a second. Why is there a minus sign in there? But do you at least see that it's 2 omega v sine phi?
Opposite of the Coriolis force.
South
Okay.
to north.
Oh, because it's a westerly drift. Because U is defined as moving in the east direction, correct?
To the east, yes. Yeah. Let me show you this on a picture. This is where it gets a little bit tougher. Okay. I'm going to draw a picture from the top down. Now let me go back to blue. I have at the center the velocity. I have this motion moving. There's an object moving that way. Right? So the Coriolis force is going to be pointing perpendicular to the right. And this is at a latitude line. But on the latitude line, do you now, this is where it gets really hard. There is a force pointing tangent to the Earth. Right, this is tangent to Earth. So if I'm standing on the Earth, which way does this force point to me if I'm standing on the Earth? If I were standing over at the North Pole, which way would that force be pointing? You can't really define it there. If I'm standing at the equator, which way would that force be pointing?
South.
No, if it's tangent to the Earth when I'm at the equator.
Oh.
which way would that force be pointing?
Meridianally?
Straight out.
It would be pointing horizontally.
Mm.
The entire thing would be pointing horizontally, right? If I'm at the North Pole, it doesn't make sense, so it has to be 0. So what I'm saying is I need some function that when the latitude is 0, the value is 1, and when I'm at 90 degrees, the value is 0. Well, what function does that?
Cosine.
Cosine, right? So what we have then is this. This is the Coriolis force. Which is 2 omega sine phi, and that is if something is moving zonally. If it's moving meridionally, then the Coriolis force is either V cosine phi or V sine phi. And this is the way that I wrote it was parallel to axis. And this is perpendicular to the axis. Now, let me get rid of this, erase the chalkboard, or the blackboard, I guess.
Minus,
It used to be.
minus parallel to axis is what that says?
No, this is just pointing, parallel.
Oh.
It's just the cosine is parallel to the axis. The sine is perpendicular to the axis. So I'm going to imagine that I have the Coriolis force. Right? Because now I'm saying I don't have, what I've done is I basically said I'm just going to look at the zonal component, and then I'm just going to look at the meridional component. Now I can put those two together. I can add those two forces together to get the total of this. Okay? So what that becomes is the Coriolis force is 2 omega sine phi times u plus v. Right? Because I factored out 2 omega sine phi from the horizontal. So that the Coriolis force is actually 2 omega sine phi, or if you'd rather say 2 omega v sine phi. And that becomes, this is the capital V. Not the little v that we had before. But which way does the force point? So I'm going to say I have a velocity that looks like this. There's my velocity vector. And I'm breaking it down into u. And actually, I put u vector. What probably a better way to do it? Ui hat. And then what's this part of the velocity?
VI hat.
No,
UJ hat.
j hat.
Oh, J hat.
VJ.
Right. So basically, what I'm saying is blue plus green equals pink. I'm breaking down the velocity into a zonal and the meridional component. Now, which way does the Coriolis force point? The Coriolis force points perpendicular to the right, and the Coriolis force points perpendicular to the right. Right? Does that make sense? That's the Coriolis force to the zonal. And this gold is the Coriolis force to meridional. But if I add the yellow and the red, like that, then the Coriolis force should point that way. So let's label this so that you know what I'm talking about. That's the big Coriolis force, the Coriolis force total. This is the
Meridional.
zonal change,
Huh?
and this is the,
You got them backwards.
well, hold on. So Jim, what I'm saying is that this is the Coriolis force in the zonal direction. See, the yellow arrow points in the zonal direction.
Oh.
The velocity is meridional, but the Coriolis force is zonal.
Okay.
And look at the red. Do you agree that that is a positive u? But which way does the Coriolis force point? Negative. That's where the negative sign comes in there. And so this gray force is going to point in that direction. Coriolis force is perpendicular to the right of motion. And as a result, we need to say, well, does that make sense? I mean, do you agree this is not simplistic, stupid stuff? This is pretty complex. Like, whoa, all because the Earth is spinning. Now, there's one thing left that we need to do for this. Is we need to make it a vector. So do you guys agree in all of this that the Coriolis force from a scalar quantity is 2 omega v sine phi? Because we're basically saying v is the magnitude of the vector. Now sometimes we go CF equals FV. Where F is called the Coriolis parameter and F is equal to 2 omega sine phi. So we're substituting 2 omega sine phi and calling it F. But how do I make CF a vector?
At z omega sine theta?
No. Z is 2.
Oh, okay, okay. I was gonna say I didn't think that was right, but
Yes, you would be correct, my friend. So how do I make the Coriolis force a vector? In other words, how do I go, this is a vector. Which way does the vector point?
$90 degrees to whatever, or right to the motion.
Right? It's always perpendicular 90 degrees to the right of the motion. So how do I do that?
Cross product?
So it's negative k, which means, and you have to kind of stand up to do this. You're going to go into the screen, cross the velocity vector, and your thumb points to the right. Because you're right? Because remember what a cross product does. A cross product always finds a vector perpendicular to the other two vectors. Since k is pointing up, we know that we want a vector that points to the right of the motion. So down cross the vector is going to be, down is negative k. And since what's the magnitude of k hat?
1.
And anything times 1, the multiplication identity property is itself. So I'm not changing the magnitude by multiplying it by 1. And that's the way the Coriolis force is determined.
Huh.
That's pretty kick-ass, isn't it?
Mm.
huh.
Okay, so questions? Now we need to do something completely different, but really good stuff. Any questions on this?
can you hold on for a second? I need to grab some more paper from downstairs. My notebook ran out of space.
All right, I'm gonna go get some coffee. Take a minute and a half. I'll be right back.
Cream only.
That should keep me going for the rest of class.
I wanted, I just thought of something. I wanted to share something that I was thinking of that's bothered me, and I don't know if it bothered you. Sometimes I go past it, I don't let you know. Why the negative sign there? Why is there that negative sign there? Because if I'm moving north, what does this become? What's the change in the radius, the apparent radius, as I move north?
Getting smaller.
So this is negative. That's negative. That acquires a positive U. I don't know if I explained that clearly.
No, now it's clear.
Does that make sense now? Allison, are you there? Okay, does that make sense? I just wanted you to. Allison, I just wanted to show you this, that the negative, so if I'm traveling to the north, my RA, the apparent radius, is getting smaller. So the value of dRA dt is less than 0. So that's so this is negative times a negative, and that becomes a positive drift. I don't think I was clear with that. Does that make sense now?
Mm-hmm.
All right, so now we've got something, and we're going to deal with natural coordinates, which is fun. And I'm going to create a, whoops, I'm going to create a box that looks like this. And I'm going to create a box that's going to be like this. That's crappy. Okay, do you see that box there?
Oh.
I am going to call the size, the length of this box, the height, delta Z. And I'm going to call this direction delta N, and this direction from there to there, that's delta S.
Which one's delta Z? Up and down?
Up and down. Now we're using natural coordinates. So what are we saying? What is this direction? What is that direction? That's the S direction. That's this positive. It's going down the streamline. And you'll see why that is in a second. Now, what I have here is I have a force acting on both sides of this box. And I'm saying that I've got pressure acting on both sides of this box. That there's a force. Now, force,
So the box is being compressed.
no. What am I doing? Sorry, this is bad notes. I had bad notes. Right? Pressure is force over area, then the force is pressure times the area. Well, what is the area?
Delta N times delta Z.
No, think of, see, I'm putting the force in the purple. So what's the area of this face? Right? I'm looking at this, the left and right sides of those boxes, of that box.
Oh, okay. Gotcha.
Okay, now, if the force on the right side is pressure plus a change in pressure, then this is the left side, right? So what's the right side? What's the right side pressure? Or the right side force? Wouldn't it be P plus delta P times delta S plus, oops, delta Z? That's assuming there's a total change in pressure. This is total change in pressure.
I want it to be negative. The force on one side.
Yeah, I guess you could put in the negative sign there. It probably makes sense to do that, wouldn't it? Because they're acting in opposite directions. So then the total change in pressure, if I'm using derivatives, Instead of using delta, what would this be?
P.
Well, I'm going to use partial because I'm only dealing with this one direction. And I'm going to say, which way is the pressure changing? In what direction? Times dN. Therefore, if I say that dP dN is constant, then the total change in pressure is equal to now, let's see what that means. And I actually, what I'd like to ask you guys is, what do you think this is? What do you think this means? What's a
It's
better
isobaric.
way to say that?
It's an isobaric change.
No. I mean, this is weird. Like, what does it mean when I'm using the partial derivative, dPdN? Again, this goes into interpretation of calculus. The calculus is the easy part, right? And look at this. If that's constant, do you agree that this comes out? That would come out of the integral. And then I'm just integrating the infinite small amount of changes of n from one place to another. Therefore, that's the total change in n. So that makes sense if this is constant. But what does that mean? Like, what is this? What does that mean?
And anywhere in the box, the pressure is constant.
No. What do you think it means, Allison?
I was thinking of it as little infinitesimal slices along the n-axis, and that they're not overall getting bigger; they're just staying the same uniformly.
So what's the relationship? If I said this, if I said dv dt equals 0, you'd say it's what?
There's no acceleration.
There's no acceleration, right? So what does that mean about the velocity?
That it's constant.
It's constant.
Well, the velocity is not constant. The change in the velocity is constant, which means the velocity is what? Like if I said graph of A versus T, you'd say there's no acceleration. What would V versus T be?
Line.
It'd be a line.
Line.
So when I have 0 acceleration, the velocity is constant. That's what this means. So if I have the change in pressure as I move in the n direction, if the change in the pressure over a change in n is constant, then what I say is that the pressure is changing linearly. So, Allison, I think that's kind of what you said, right? Meaning, if over this course of distance it's 4 millibars, I go a quarter of the way over, I'm dropping 1 millibar. I go another way, I'm dropping another millibar. So it's a linear constant. Now, do you think that's good? Do you think that pressure on the large scale drops linearly?
No.
No, that's probably not a good guess. But on a short distance, that's what we assume. We assume that pressure changes linearly. Now, what is the mass? What is the mass of that parcel? What do you think?
Oops.
How many times do I do that? All the time.
Every day.
What?
It's constant.
Isn't it the density,
That's rho. Okay.
which is mass over volume, times the volume?
What I said.
Okay? So the pressure gradient force
Ooh, we're getting to that.
is going to be equal to I'm going to say the pressure gradient force is acting in the normal direction, right? Which is going to be equal to minus the mass times the change in the pressure, which is the mass times dP dN times delta N. But the mass is rho times delta N times delta S times delta Z. Hold on. My bad. I'm not so fluent in this. What I want to think about is that force is mass times acceleration, right? And we know the mass, but we know the mass was density times delta N times delta S times delta Z. We need to put that in the bottom because we want acceleration is force over mass. And the force is going to be the pressure times the area. So the pressure is dPdN times delta N times the area, which was delta S times delta Z. And then what happens to this? So that the pressure gradient
It's 1 over rho dP dZ.
is 1 over rho dPdN. But which way does the pressure gradient point? Like Allison set out, this is a larger pressure, which is in the negative direction. So we need to put a minus sign in there. And now we've come up with, in natural coordinates, the pressure gradient force. And what that means is that the flow has got to be going in this direction, right? It's going into the box because that's where the streamline is. The force is going to be the change in pressure negatively because it points from what? Which way does the pressure gradient force point? From high to low. So the pressure gradient force is pointing in this idea. Oh, actually, you know what? I want to use this color. Go back to my, that is the pressure gradient force. But what points to the right? Coriolis force. And I could put in vectors. So what I'm going to say is that the geostrophic wind is minus 1 over rho dp dn equals 2 omega b sine phi, which is geostrophic. This is the PGF in natural coordinates.
And that's negative 1 p over times the d. Negative 1p dp over dn is
Minus what?
the first part of that equation is the pressure gradient force, right?
Yeah, but what does it read it?
Negative 1 over rho.
Well, that's a whole lot different than what you said.
Yeah.
Negative 1 over rho.
I realized I did that. And I was like, ah, crap.
Right. Okay. I just wanted to make sure you figured that out. So
Yeah.
negative 1 over rho dp dn equals 2 omega b sine phi.
Then dp to dn, yeah. Okay. So, crap, Paul's going to roast me.
And it points from high to low pressure. Because how does the pressure change? Look at this. If that's the case, do you agree that there is, according to this, there's higher pressure over there and lower pressure on this side? So the pressure gradient force points from high to low, which means the bias bow low with the wind at my back, low pressures to my left, which is going in the negative n direction. So the pressure goes down in the negative n direction. And then that's going to be balanced by 2 omega b sine phi. Now, what time is it? I got time. I got one more thing, and I'm going to go pretty quickly through this. Any questions on this graph so far? All right, so let's try this. Delta P is going to be dp dn times delta n. Do you agree with this? That's what we just showed. But do you understand that there's another pressure gradient force? Which way does that pressure gradient force?
That's upward.
Okay, so that would be, how would I write that? If I'm thinking a little bit broader now. Would it be the same thing? However, if we are on an isobaric surface, what's delta P equal to? Right, Mike? I think you said it. Your mic's not working, but it looked like you said 0.
Yeah.
Okay? Which means that dP dN times delta N is equal to minus dP dZ times delta Z.
Did you mean to write that above?
What?
I think you forgot to write the DZ up above. You wrote dPdN times DZ.
dP dN times delta N equals, oh, I'm sorry. Thank you. That's what I wanted. You guys see that change? So this is assuming I'm on an isobaric surface, which is what we're going to. Now, delta Z over delta N is going to equal what? Now here is where we do not cancel out the DPs, right? I kind of want to make this point to you. Because dP dN is one entity. Okay, so what I'm saying in this scenario is that the numerator says, how does the pressure change in the N direction? Remember, N is going to be horizontal, right? And then dP dZ is how does pressure change as you go up? But this is on an isobaric surface. So what is delta Z over delta N? What is delta Z over delta N? Isn't this going to be delta Z? And this is going to be delta N. And this is going to be up. So delta Z over delta N is actually what? Nick, what would you say that is? I mean, just qualitatively. I'm not looking for a number. Anybody? Look at the picture. What is this blue thing?
Rhombus.
No. What is the blue thing supposed to represent?
Isobaric surface.
Right.
Surface.
So this delta Z over delta N is what?
Oh.
Isn't it?
Oh, because
Slope of the isobaric surface.
Yeah.
And I can say, I can put this into differentials by saying dz dn p is constant. What is dp dn?
So those both of those terms, the slope of the isobaric surface and the pressure gradient forces, are both negative?
Oh, that's a good point.
Or
I'm sorry, Nick. Where are you talking?
the equation del
Here?
z over del n, yeah, equals, there's negative sides on both sides. Is there supposed, where's the negative sign
No,
supposed to
I'm
be?
sorry. This is just what this is.
Oh, you were pointing it. Okay, I see.
That's that. Sorry.
It's all right.
If you misconstrued that, I can understand that.
Mm-hmm.
So I'm saying that's the slope of the isobaric surface. Now, would you agree that when I have an isobaric surface, the pressure change over n is going to be a whole lot smaller than the pressure change as you go up? So the denominator is way bigger than the numerator, which means the slope is really small, which would make sense because if I look on a weather map, I could be looking at 60 meters change over like 400 kilometers, right? That's a really small number, but that's the size of the pressure gradient force. So what I'm saying is that dP dN is much smaller than dP dZ. Pressure changes a lot more. But how much? Is dP dZ? Right? Hydrostatic. We know that pressure gradient is hydrostatic. So what I can write on here, and I'm going to erase this whole thing because this is the key part. I'm saying that dz dn on a constant pressure surface, isobaric surface, is equal to dP dn over rho g. But g times dz dn on a constant pressure surface is equal to 1 over rho dP dn. So the pressure gradient force in normal or natural coordinates is minus 1 over rho dP dn, which is equal to minus g dz dn. But we know that g times dz is equal to d phi, which is equal to g naught times d capital Z. So we can say that's equal to geopotential change, which is equal to minus G naught geopotential height change. Which is what we've talked about before. So we said in one of my classes, what did we say? We said the greater the pressure gradient, the greater the height gradient. And when I say height gradient, what is this? What should I be saying? Not just height gradient, but what should I say?
Geopotential.
Geopotential height, which leads to the greater the wind. Well, actually, there's one in the middle there. The greater the slope of the isobaric surface. Because that's what we're talking about, aren't we? The greater the wind. We've done this in some of my classes. You should have had this someplace in there. This is what we call the thermal wind equation. And then we have to go backwards, which we'll do later, to say, well, what causes the pressure gradient, the isobaric surface slope? It's a thickness gradient. But bottom line is this. When I look at our models, and I'm looking at 500 millibar heights, I am looking at geopotential height, which are these black lines. Now, why do I use them in the upper atmosphere? Because when I use them in the upper atmosphere, what's the only thing I need to know? G naught. If I use pressure gradient in the upper atmosphere, what do I need to know? The density. That's not something I want to deal with all the time. So by using this, I'm using geopotential height, and all I need is gravity. And that's an easy calculation, 9.81 meters per second squared. If I use pressure gradients, then I need to know the density. So I need to know, well, what pressure am I at, and what's the temperature? Where does that make sense? Well, it makes sense at the ground. Why does it make sense at the ground? Because I don't want to deal with height because the ground goes up and down. So I can deal with pressure. I can measure the temperature, therefore I know the density. Last thing before Thanksgiving break. Any questions on this?
Nope.
Okay, last thing before break is that in Cartesian coordinates, I have that the pressure gradient force is equal to minus 1 over rho times but we know that that's equal to minus 1 over rho times the gradient of pressure. Sorry? It's a vector. And that's what it is. because this is del acting on a scalar, which is a gradient. Okay, now I think what I'm going to give you next week is I'm going to do the continuity equation, which we've already kind of done, but we're going to go a little bit more formal, and then we're going to do geostrophic wind and gradient wind and all that other fun stuff. But I can do that on my own. So I'm going to do so remind me next week to do the geostrophic wind. Okay? Where are you guys? Hold on. I lost you. Oh, here. There. What do you think, guys? Now, Allison, you're going to be home. Are you going to be around?
Yeah.
Okay, that's fun.
Yeah.
And you don't go back till January?
Yeah.
Okay. I want the rest of you to send me this problem. It's 7.16. You get the right answers?
7.16?
Yeah, that's the one I assigned you last week or last.
Oh, yeah.
Well,
Yeah, that.
Send it to me.
Find that around here. My room's just a real big mess right now.
Okay, so is everybody good? How's it going, Mike?
Going well, going well.
Good.
Get out of trouble.
So when we get back, we've got 2 weeks. We have the geostrophic and gradient wind. We have mass continuity. We'll do some thermal wind. We'll do a little bit of the large scale stuff in the next chapter 8. So you should have all of chapter 7 kind of read. And there's obviously a lot of stuff that goes into your final notebook. Now you're getting a little bit more that you can add to it. So it would be nice if by next week you had everything done except for the things we are still to do in class. And I think that's what we need to do.
Now, with the final notebook, how much that's not on the sheet can we add, or is that allowed? Or what are your thoughts? What are the parameters?
You should, okay, so on that sheet, we have done a lot. So you need to kind of recreate your notes to do that, like the geostrophic wind. We'll talk a little bit more about that. So that won't be done. All the thermodynamic stuff is done. There's a bunch of stuff on there that you do independent research, cloud types, that kind of thing. If there's something that you're like, I don't even know what this is, then we're going to get to it.
Okay, I got, because the one thing I was thinking of is that after taking years of your forecasting class, I was thinking about if Paul Servaka's forecasting tips or something because that to me.
Yeah, anything you can put together. This is like, in a lot of programs, people put a portfolio. What are the things you've learned while at COD? So this is your chance to go crazy and go, this is what I have. In fact, I would suggest that it's probably best to put everything together in one place so that you've got this 200-page notebook of just your stuff and then get rid of all your other miscellaneous stuff.
I've actually used mine from when I took Meso, and I actually showed my dynamics professor, because I say like the stuff that we learn and then they don't believe me, and then I show them all the notes that I typed up from Meso, and they're like, oh my God.
Yeah.
Study partner.
Severe weather preparation. I've got so many notes from that still saved to this computer. It's pretty great. I didn't realize how many I'd taken last semester.
I wish I could teach. I wish I could have you guys in Meso. I wish I could do Meso with you guys. I'd like to do it. I know I might not teach that course again, but boy, it would be fun to do it on this format with you guys. I'm telling you, I can't tell you how much you've saved my semester. I look forward to Tuesday and Thursday mornings at 9 more than anything I do. Because it's so fun to do the nitty gritty of what meteorology is. Are you glad you chose this as a major?
Sure.
Yeah, it's gonna be I'm still got a ways to go for it, but I definitely think it's going to be something I enjoy doing.
It's good stuff, and I like this stuff. And Allison, it's so funny. I didn't realize how much dynamics I was helping you guys with. Not because I always thought of this as thermodynamics as a middle of the course, intermediate. But when people go away, like Brett Compton goes, everybody in the class was asking him to teach the dynamics because of what they did in my class, which was kind of crazy. So it's fun that you guys are doing this as sophomores, technically. But whatever. All right, guys, have a wonderful Thanksgiving. Allison, be safe in your drive home. The weather should be fine. The snow has stopped. It's melting already. So we'll talk to you. Have a great Thanksgiving.
All right, time to get a bunch of my
Happy
homework done
Thanksgiving.
this Thanksgiving break. I'm gonna get a lot of it done.
Okay, sounds good, guys. Have a good one.
You
Take
too,
care.
Paul. Take care, everyone.
Have
Bye.
a happy Thanksgiving.